Maths Mocks 2022, Paper 1. If you like what you see, I'd be very grateful if you could click on the subscribe to the Tulla Maths page on the bottom right hand corner. So Paper 1, Question 1a, solve the simultaneous equation. So here we have the equation of a line and a curve. We don't need to actually manipulate the equation of the line. We can just sub it straight into our curve. So I'm basically subbing in 2y minus 10 for x. So I'm going to do that now. So everywhere I have an x, I'm just putting in my brackets. And I'm going to sub in 2y minus 10, 2y minus 10 for x. In the first set of brackets, I need to multiply them by itself because it's squared. And in the second one, I'm just going to put the factor, the y, or the multiple, the y to the front of the bracket, but just because we're more used to multiplying from the front rather than the rear of the bracket. So multiplying out my brackets here, first term by second bracket, second term by second bracket, then multiplying in the minus y into this bracket, and I get minus 2y squared, positive 10y equals minus 12. Multiplying in this first bracket now, I'm getting a 4y squared minus 20y. Multiplying the second bracket, I get minus 20y again. And minus 10 by minus 10 is positive 100. Minus 2y squared plus 10y. And now I'm just going to add 12 to both sides, or just move that 12 over to become a positive 12 equals to 0. Tidying things up a little bit here now, I'm going to group the y squareds. That's giving me 2y squared. I'm going to group the y's, minus 20, minus 40, minus 30. And then my constants is 100 plus 12, which is plus 112 equals to 0. I can see here that if I divide across by 2, it'll make it a little bit easier for myself. So that will become y squared minus 15y plus 56 is equal to 0. Doing my two brackets, solving these quadratic equation, that's giving me multiples of 56 that add to minus 15 are minus 8 and minus 7. So y minus 7, my y minus 8 are my factors. Solving now for my roots, I have y minus 7 is equal to 0. Moving over to 7, I get y is equal to positive 7. Y minus 8 is equal to 0. Moving over to minus 8, I get y is equal to positive 8. So there are my two values for y. Now I need to solve for x. So to get x, I'm coming back to the very start of the question. They tell me that x is equal to 2y minus 10. And I'm going to do it out twice because I need to do it for y is equal to 7 and y is equal to positive 8. And subbing in my value for y, so 2 times minus 10, x is equal to 2 times minus 10. In the first one, I'm going to sub in my 7, and in the second one, I'm subbing in my 8. Solving that now, that gives me x is equal to 14 minus 10, which is 4. So my first point is 4, which corresponds to 7 as my y. And my second value for x is 16 minus 10, which is 6. So my point there is 6 as x, 8 as y. So they're my 2 points. They're my 2 points of intersection. Question 1b, solve x squared plus x minus 10 less than or equal to 10. So we're on to our inequalities now. The only part there I think that's just might catch us out is the less than or equal to 10 on the right. So first thing I would do is move over that 10 or subtract 10 from both sides basically. So that would leave me with x squared plus x minus 10 less than or equal to 0. So x squared plus 1x minus 20 is less than or equal to 0. I'm now going to get my factors and I'm going to let that equal to 0 because I just want to find out first of all where it crosses the x-axis, and then I'll worry about my inequality sign. So the factors of minus 20 that add to 1 are positive 5 and negative 4. So positive 5 multiplied by negative 4 is negative 20. 5 take away 4 is 1. Solving these now for my roots, I have x plus 5 is equal to 0, x is equal to negative 5, and I have x minus 4 is equal to 0, and x is equal to positive 4. So let's have a look on my coordinate graph, how they would sit for me. So my first root there is, let's say, positive 4, negative 5. So this is just a quick sketch of what it might look like. It's a positive quadratic, so it'll go through my first root and then my second. So my inequality is less than or equal to 0. So that means I'm looking for the region below the x-axis. So I'm basically looking for this region here. And as an inequality, x in this portion will fall between positive 4 and negative 5. And the question is less than or equal to 0. So that's why I'm using the less than or equal to symbol. So from minus 5 to positive 4, all values of x elements of the real. So in part C, prove that a squared plus 5b squared greater than or equal to 2ab for all values of a and b an element of R. Same thing again here. I'm going to first of all move over that 2ab. So I'm going to put the 2ab in the center. So that will become a negative 2ab plus my 5b squared. And I need to solve this now. So I need to just show that this is greater than 0. So the way we want to do these is basically get something squared. In order to do that, I'm going to maybe use my completing the square. It's the best way of showing something squared. My two brackets here, just so you can see a little bit of revision, are a and a. So I need two numbers that multiplied by a. By a is giving me a squared. So just look in the center one here. I have it written as minus 2ab. I'm just going to rearrange that. You don't have to, but I'm going to write it as 2ba plus 5b squared. So I'm just going to change that second one ever so slightly. Now I'm going to complete my square. Completing the square tells me to divide the coefficient of the x minus 2b, divide it by 2, and square that value. So that's getting me minus 1b all to be squared. Minus by minus is plus, b by b is positive b squared. So I'm now going to come over and I'm going to rewrite my quadratic. A squared minus 2ba, and now I'm going to add and subtract my b squared. So plus b squared minus b squared, because that's still 0, plus 5b squared greater than or equal to 0. I'm then going to factorize this part, and my factors are b by b are the only two to get me to b squared. And if you're in doubt, just multiply them out yourself and you should get minus 2ba. So a by a is a squared, b by b, b squared, and then you should get minus 1ab, which is minus 2ab. Don't forget, we also have this part here, minus b squared plus 5b squared, which is giving me positive 4b squared greater than 0. I can then put these two parts together. It's the same factor multiplied by itself, so I'm going to write it as a square plus 4b squared. And we are done, because you can see here I have a minus b all to be squared, so a squared must be positive. So let's just write that down. A square must be positive. And 4b squared again is a positive, so that's why I am complete. So therefore I am happy that a squared plus 5b squared is greater than 2ab. That is part C done. So question 2a, the complex numbers z1 and z2 are plotted on the Argand diagram for the complex plane with z is equal to x plus I times y. On the Argand diagram above, plot the following points and ensure they're clearly labelled. So z3. z3 is found by multiplying z2 by I. Now let's just assume that z2 is back 2 units on the real and up 4 on the imaginary. So the complex number there could be something like minus 2 plus 4i. And I want to multiply that by I, so if I times that by I. Now a quicker way of doing this is just the knowledge of multiplying by I rotates anti-clockwise by 90 degrees, but let's do it this way just to show. So that becomes minus 2i plus 4 times minus 1, which is minus 2i minus 4, which is the same as minus 4 minus 2i. Now if we plot that on the Argand diagram, where would that go? So I'd have to go out to minus 4 on the real and down to minus 2 on the imaginary. So the complex number would be here. So I'm just going to delete all the rough work there just so you can see that clearly. So the complex number z3 would be here. Now again, as I said, you could also do that by noticing that multiplying by I rotates by 90 degrees. So you could have done it that way either. The next complex number we need to plot is Z4. And Z4 is found by multiplying Z3 by -1. Now that basically just reflects it across the origin. So just imagine we had a line coming through here, and it's basically just going to reflect it to the other side of that line. It's basically symmetrical. So where would that go? So let's just examine Z3 for a second. Z3, as we said, is -4 minus 2i. All you're doing basically is multiplying that by a -1. That's what the minus times Z3 means. So if I multiply in that minus, you will notice here that it's just changing it to a 4 plus 2i. So I would go out to 4, 1, 2, 3, 4 on the real, up to 2 on the imaginary. So my complex number Z4 would be located here. And the final one, Z5, where Z5 is the conjugate of Z4. So Z4, as we have it written down here, is 4 plus 2i. We'll just call that Z4. The conjugate is basically when you change the sign attached to the imaginary part. So that becomes 4 minus 2i. So basically, I'm going back, I'm staying up on the positive 4 on the real, but I'm going down to -2i, which would be here. So my complex number Z5 would be 4 minus 2i. And that's part A complete. B part 1, use De Moivre's theorem to express cos theta plus I sine theta to the power of 3 in the form cos k theta plus I sine k theta. So I'm going to my log tables here on page 20, taking down my rule for De Moivre's theorem, which is written as cos theta plus I sine theta to the power of n is the same as, equals to, cos n theta, n standing for the power, I sine n theta. So that's what the log tables tells me. So basically here I'm just looking at my power. So the question is to the power of 3. I have n as my power, so I'm basically substituting 3 in for n. So I have cos theta plus I sine theta all to the power of 3. And what's that the same as? That's the same as cos 3 theta plus I sine 3 theta. So I'm just basically putting my power of 3 in for n. And that's basically what they wanted us to do. So basically in this question, k is equal to 3. K is my power here. That's B part 1. Scrolling down now to B part 2. Use binomial theorem, or otherwise to expand cos theta plus I sine theta to the power of 3. The otherwise method there is to multiply itself by itself 3 times. That's the approach I'm going to take just to practice our algebra skills here, but by all means go to your log tables and use your binomial theorem, but it's cos theta plus I sine theta by itself 3 times. Okay, so first thing I'm going to do here is basically multiply out the first two on their own. So multiplying these, I get, opening up the brackets, first term by second bracket, and then second term plus I sine theta by my second bracket. So that's what I'm going to do out first. So I'm just going to put that into a square bracket, and then I'm going to multiply it by the cos theta plus I sine theta as my third bracket. So multiplying this out, multiplying it in, I'm getting cos squared theta, because cos theta by cos theta is cos squared theta, plus cos theta by sine just becomes sine theta cos theta, or in the other order. Multiplying in the second bracket, I sine theta by cos theta is giving me plus I sine theta cos theta, and then multiplying in the I sine theta by I sine theta would give me I squared for I by I, sine squared theta for sine theta by sine theta. So that's the first two brackets multiplied out, and then don't forget multiplying it by the third one now in a couple of minutes. Tidying up the first one, let's start grouping things together or changing I squared to -1. So see this or this I squared. I'm going to change that to a minus 1 now in a second. I can put I sine theta cos theta plus I sine theta cos theta together to give me 2 of them. So tidying all this up, I get cos squared theta plus 2I sine theta cos theta, and then the I squared will become negative 1, so that'll give me negative 1 by sine squared theta, which is just negative sine squared theta. So that's my first 2 brackets done. Let's now multiply it by the third bracket. So I'm going to multiply in this third bracket. So basically expanding the brackets once again. So I'm going to multiply cos theta by all of this in blue, which is my cos squared theta plus 2I sine theta cos theta minus sine squared theta. Then I'm going to multiply the second term, which is my plus I sine theta, by, again, my full bracket in blue, which is cos squared theta plus 2I sine theta cos theta minus sine squared theta. So again, like we said, this is just advanced algebra really. Multiplying in my first bracket. So what are we getting there? Cos theta by cos squared theta is cos cubed theta. Cos theta by 2I sine theta cos theta is giving me plus 2I sine theta, don't change. Cos theta by cos theta gives me cos squared theta. And my final jump there is my cos theta by minus sine squared theta will give me negative sine squared theta cos theta. Okay, next bracket, second bracket. I sine theta by cos squared theta is giving me plus I sine theta cos theta. Then multiplying the I sine theta by the 2I sine theta cos theta, well, I have the 2. I by I will give me I squared. Sine theta by sine theta will give me sine squared theta times cos theta. And the final one is I sine theta by the minus sine squared theta, which is giving me minus by plus is minus. I sine theta by sine squared theta gives me a cubed sine theta. Okay, so let's see, can we tidy this up now a wee bit? The only thing I can see there is the I squared here. We can change to a negative 1. So rewriting this whole line is going to give me cos cubed theta plus 2I sine theta cos squared theta minus sine squared theta cos theta plus I sine theta cos theta, and the I squared will become negative 1. Negative 1 by 2 is negative 2 sine squared theta cos theta minus I sine cubed theta. And I think that is as far as we can go there with our multiplying out. So that will be part 2. Having a look at part 3 now to this, it says, hence prove that cos 3 theta is equal to 4 cos 3 theta minus 3 cos theta. So we're going to need our answer here now from part 2. The question is getting us to focus in on the cos 3 theta part of my De Moivre's theorem. So basically I'm looking for the real parts, because remember De Moivre's theorem is cos theta plus I sine theta. So they're only getting us to look at or investigate one part of it, which is the cos part, which is the real part. So basically I need to ignore anything with an I in it. So this one here has an I, so I'm going to ignore that. I have an I here, I'm going to ignore that. And I have an I here in the last one, so I'm going to ignore that. So in part 3, the only part that I need here is cos 3 theta, which is going to be equal to this part, and this part. Anything without an I, basically, the real part. So cos 3 theta minus sine squared theta cos theta, and minus 2 sine squared theta cos theta. So that's what I have. I now need to manipulate this or change it so it looks like 4 cos theta cubed minus 3 cos theta. So basically I want it in terms of cos. I want to get rid of any sine. But you can see here, I have a sine here. I have a sine squared, and I also have another sine squared here. So I want to basically change those around. Let's see, can we write them in terms of cos? So from our log tables, we know that sine squared a plus cos squared a is equal to 1. So I'm using that piece of information. So that's from my log tables. So basically what I'm going to do here is I'm going to use that. I'm going to move over the cos squared a. So that means that sine squared a is the same as 1 minus cos squared a. So that's what I'm going to sub in for sine squared a, or in our case, sine squared theta. So let's have a look. Cos 3 theta is equal to cos cubed theta minus, now I'm going to substitute in 1 minus cos squared theta, and then I have to multiply that by the cos theta that's already in it, minus 2 multiplied by sine squared theta. I'm now changing that once again to 1 minus cos squared theta, and I need to multiply that by the cos theta. So a little bit tidying up here now. I'm going to multiply in the minus into the bracket, and I'm also going to multiply the cos into the bracket. So if I multiply the minus by the cos, I get minus cos. So minus cos by the 1 will give me minus cos theta, and the minus cos by the minus cos squared will give me a plus cos cubed theta. So that's when I multiply in my bracket. Let's multiply in the second bracket. So let's first of all multiply the cos by the minus 2 to give me minus 2 cos theta. Then multiply that into the bracket. So that's giving me minus 2 cos theta. And then minus by minus will give me a plus 2 cos cubed theta when I multiply in the bracket. And again, I'm trying to get that to equal 3 cos theta. Or sorry, cos theta cubed. Anything we can put together, let's see. So we have cos cubed theta here, a cos cubed theta here, and 2 cos thetas here. So adding them together, that gives me 4 of them. So 4 cos theta cubed. And then I have a minus cos theta and a negative 2 cos theta. So minus 1 minus 2 gives me minus 3 of them. Cos theta is equal to cos theta cubed. And looking back up to the question, that's what they wanted. They wanted us to get it equal to 4 cos theta cubed minus 3 cos theta. And that's what we've done. So we really needed part 2 of that question there to help us. Part 2 could have been done by multiplying out the brackets like we said, that I've done. Or you could have used your binomial theorem from your log tables, whichever suits. Question 3, part of the graph of the curve with the equation y is equal to e to the x is shown. Part A, complete the table by calculating each value corrected 2 decimal points. This is basically just calculator work. What we basically have to do now is we have to take our equation here, so take the e to the power of x, and we have our values for x in the table. So we basically just need to input these into the equation. So for example, if I want to find the value that goes in here, I basically go to my calculator, I go e to the power of 1.5, and the e is found by pressing the alpha key and then pressing the multiply by 10. It's down to the right hand side of the decimal button on your calculator. So it's the red e you're trying to get up in your calculator, and that gives me a value of 4.48. So it's basically just calculator work here. So if I fill in the rest of them, e to the power of a half is 1.65, e to the power of 1 is 2.72, and e to the power of 2 is 7.39. That's all they've wanted us to do there on part A. As we look at part B now, they want us to basically get the area of the curve. So it's asking us to use the trapezoidal rule. So the trapezoidal rule is found in our log tables on page 12, with all the values in the completed table to find an approximate value for the area of the region bound by the x-axis, the y-axis, the function, and the line y is equal to 2. So where would that be on our graph? So bound by the x-axis is this area here. Bound by the y-axis, again, is this area here. But it then tells us that it also wants us to go to the curve, which is here, and x is equal to 2. So x is equal to 2 here. X is equal to 2. So that's a vertical line going up our page, basically. So in other words, they basically want us to get, so if we rub all this out, the area of the curve from 2 to where it hits the curve, then where it hits the x-axis, and then we come back over to where it hits the curve again, which is here. So they basically just want us to get the area of that region in here. So let's fill in the formula from our log tables first of all. So it's given as A is equal to, so A stands for area, H over 2 multiplied by y1 plus yn plus 2 times all of the other heights. So y2 plus so on and so on and so on up until the second last height. And we need to mark in some pieces of information here. So the H is the vertical distance, the distance between any two units. And what we're going to do here, that's the value for x. So here you can see that the distance between them is a half. It's going up in half units. So on my picture, it's going up in halves basically. So that's my H. So as I fill that in, I would have 0.5 over 2. Bracket y1. Y1 stands for my first height. So my first height where they want me to start at, they've given us in the table here as 1. So if I come back up to my picture actually, they want me to start the area of the curve that they actually want me to find is not actually the full curve. They actually just want me to get this part of the curve. That's all they want me to get the area of, because they want me to start at 0 where it joins the y-axis. So filling that in, I have 0.5 over 2, y1 would be 1, plus my last height, which would be 7.39, plus 2 times all of the other heights. So 1.65 plus 2.72 plus 4.48. That's my second last height. When I type that into my calculator, I get 0.25 times 8.39 plus, and then I'll do this part out on my calculator, 2 multiplied by all of this bracket, which is 17.7. So that's 0.25 times 26.09. And when I multiply 26.09 by a quarter on my calculator, I'm getting 6.52 square units. And that's the area under the curve using the trapezoidal rule. The next part of that question, part C, wants us to use integration. So use integration to find the exact value for the area of the region described in part B. Give your answer to 2 decimals. So the first thing we do is write down our function y is equal to e to the x. We need to differentiate that. So I'm using my log tables now on page 26. So to differentiate e to the power of x, well, you'll see that the integral of that is just e to the power of x. Sorry, I'm integrating, not differentiating, I should say. So I now need to get my integrals from e to the power of x from 2 to 0. So they're coming from my table, the values on the x for my curve. So it starts at 0 and ends at 2. So I'm basically just subbing in 2 for x, so e to the power of x, and then I'm subtracting e to the 0. And that will get me the area under the curve. So the area there is coming out when I use my calculator as 6.39 units squared, or square units. So that's the exact area for the area under the curve. Part B then wants us to find the percentage error between the approximate and the exact. So the formula I use is difference over original times by 100 over 1, and that'll give us the percentage. Now the difference is when I take my exact and my estimate away from each other. So the estimated area was 6.52 and I take away my exact 6.39, so that'll give me the difference between the two of them. I divide that by the original, which is the true value, 6.39, and then I turn that into percentage by timesing it by 100 over 1. And I'll just bring it up here. So when I take them away, I get 0.13. Divide that by the original, which is the exact, times by 100 over 1, which is giving me, and it's asking you to the nearest percentage, which is equal to 2%. So there's my percentage error, 2%. Looking now at part E, if y is equal to f of x, by plotting the line y is equal to x or otherwise, draw the function of f inverse x. So we're looking at the inverse here. So I'm actually just going to go back up to my picture here for a few minutes to look at this. So the first thing we could do here is it's asking us to plot the line y is equal to x. So that's the first thing I'm going to do. So with my ruler, I'd be drawing y is equal to x. So that's for every input, my output is the same. So again, this is just kind of rough here because I'm on a computer screen, but it should be going through the corners of each of the boxes. So y is equal to x, and the same for the negatives. So that's the line, y is equal to x. Now my inverse coordinates are basically just the opposites or the reverse of the couples that I already have. Now the couples are basically just the coordinates. So I'm just going to list out my coordinates here. What do we have? We have 0, 1. We have a half 1.65. We have 1, 2.72. Again, you can do this by visual, but I'm just going to take the long route here by actually doing it by coordinates. 4.48 and 2, 7.39. So they're my original couples. Now the inverse of these is by basically just reverting them, swapping the values of x's and y's. So my inverse coordinate here would be 1, 0, 1.65, 0.5. My input here would be 2.72 and I'd get out 1. That would be now my new output. I'd put in 4.48, I'd get out 1. And I'd put in 7.39 and I'd get out 2. Sorry, that's a 1.5 there actually, isn't it? For my second to last one. So they're the new couples that I basically need to plot. So where would they go? 1, 0 would be here. 1.65 to a half would go roughly about there. 2.72 to 1, again, these are just estimate. 4.48, roughly 4.5 up to 1.5 there. And the final one, which is off out a little bit further, 7.39 up to 2. So we're going out about there really. But let's go in the opposite direction. So you can kind of see the shape of my curve now. It's looking something like that, and hopefully you can follow the other curve now. So it's going to kind of come down here, but not cross the y-axis. So that would be my inverse of the original y is equal to e to the x. Basically try and think of this as like butterfly wings. If I fold that black curve over the red line, the y is equal to x, it should map onto the blue one. So you're basically just drawing the mirror image of it if I was to fold it over the y is equal to x line. So really, when I come back down to part E here, I don't have too much information to write in here. I've done it all really on the picture and a little bit of rough work to the side of the picture. And that's the end of question 3. Question 4. Below is the plot of the function f of x. Part A, on the same graph, draw the function g of x, which is x minus 3 modulus minus 1. Okay, so basically what we're doing here is we're just subbing in values for x from our graph and subbing them in. So the values I'm going to sub in are going to range from maybe -1. We could go all the way up to 6, 7 or 8 if we wish, but let's start at -1 and work our way up and see can we spot maybe a pattern happening with the shapes. So let's begin. Let x is equal to -1 first of all. So I'm subbing that in. So my function f or g of x is going to be x minus 3 minus 1. Subbing in -1 for x minus 3, then subtract 1. -1 minus 3 is giving me -4 modulus. Then I'm going to subtract 1. But the modulus of -4 is +4. And I'm going to subtract 1, which is 3. So my first coordinate there is going to be x is equal to, when x is -1, my point is -1, 3. So plotting that, I'm getting a coordinate here. Let's go then and try x is equal to 0. So let x is equal to 0. Same principle apply here. So the modulus of x minus 3, subtract 1. So that'll be subbing in 0 for x, subtract 3, subtract 1. So I get -3 modulus, subtract 1. -3 modulus turns into positive. So 3 take away 1 is 2. So my coordinate there is x as 0, output y as 2. So 0, 2 is here. Let's skip 1 and 2, because we can hopefully see a pattern here. Let's jump straight to letting x is equal to 3. So you can do all of them if you wish, but I'm just saving a bit of time here. So let x is equal to 3. So modulus x minus 3 minus 1, subbing x in as 3, and I get 0 minus 1, which is minus 1. So my couple there, or my point, is x as 3, output y as 0, which goes, output is minus 1, I should say, not 0. Changing that to a minus 1, 3 minus 1, which goes here. And you can see now, if I was to connect my 3 dots, or all 5, if you drew all 5, it would look something like that. So my graph is basically just being transformed by pulling it down 1 unit. Let's keep going, we'll fill in a few more. Let's try x is equal to positive 5 now. So let x is equal to 5. So x minus 3 minus 1, subbing in 5 for x, we get 2 minus 1, modulus of positive 2 is 2, so I get a point of 1 for my output. So my couple there is 5, 1, and I plot that, and you can see the same pattern is occurring as I go up from positive 3. So I go here, here, and I will go through the corners of these boxes. So that's on the same graph, draw the function g of x. Again, you can plot all points, but hopefully you can see that the pattern is occurring here. Part B, by drawing the function h of x, where x is an element of the reals, or otherwise find the coordinates of the 2 points where f of x and h of x equal, or where they cross, basically. That's what it wants us to do. Same thing again here. I'm going to basically just sub values in for x. So I'm going to start at minus 1 again, so x is equal to minus 1. And I'm subbing them now into h of x, and h of x is 2x minus 3. So I get, subbing in minus 1, I get 2 minus 1, subtract 3, gives me minus 2 subtract 3, which is minus 5 modulus, which is positive 5. So my couple there, or my point, will be minus 1, 5. So I'm going to do that the whole way up to maybe 4. So I'm now going to do x is equal to 0. I'm going to skip it here. What I get as my output there is 3. So my couple is 0, 3. When I do x is equal to 1, I get an output of 1. So my couple there is 1, 1, my coordinate. I'm now going to just practice another one. X is equal to 2. So that would be subbing into h of x. So that'd be 2 times 2 minus 3, which is the modulus of 4, take away 3, which is positive 1. So my point there would be output, or input 2, output 1. So 2, 1. And let's go through the remainders. What happens when I input 3? I get an output of 3. So my point there would be 3, 3. And a final one, what happens when we put in x is 4? I get an output of 5. So my point would be 4, 5. Okay, so hopefully they make a bit of sense. Now I'm going to go up because it says by drawing them onto the graph. So we now need to plot those couples, those points. So the first one, minus 1, 5. Minus 1, 5 would be around here. The next one, 0, 3 would be here. 1, 1 would be here. 2, 1 would be here. So hopefully you can see now, this has to create the V effect. So it has to come down and touch my axis here. So if you want to figure that one out, just do out another one here. Let x is equal to 1.5. And when you let x is equal to 1.5, you get an output of 0, so 1.50. So no harm doing that extra one, just so you can visualize that it actually creates that V effect and then bounces off the x-axis to come back up. Where were we subbing them in? So that was 2, 1, 3, 3 was my next one. And then my final one, I think we finished at 4, 5, wasn't it? Which would be here. So my graph would continue to come up. Again, it's just a sketch. And what's it asking us? The question then wants us to find the coordinates of where f of x and h of x meet. So f of x and h of x. So h of x is my red one, and my f of x is my original function, which is in the black. So that's my f of x. So where do they meet? They're meeting here and here. So those coordinates are meeting at 0, 3 and 2, 1. Wouldn't that be right? So just writing that into my answer. So therefore, the points of intersection are 0, 3 and 2, 1. Okay, looking at C, solve the inequality. So solving the inequality, in order to get rid of a modulus, don't forget you have to square both sides because you want to basically turn it to a positive value. So that's the key for evaluating the modulus of inequalities. So I'm going to basically come along, I'm going to put both sides into a bracket and square both sides, because again, that also impacts on our inequality sign, because we know that it could be positive or negative. So squaring both sides will give me 2x minus 3 times 2x minus 3 greater than or equal to x minus 3 times x minus 3. Multiplying out my two brackets, so first term times the second bracket, and then second term times the second bracket, greater than or equal to x times x minus 3, second term times the second bracket. And when I multiply them out, I'm getting 4x squared minus 6x minus 6x plus 9 greater than or equal to x squared minus 3x positive 9. And when I move everything to the left hand side and tidy it up a wee bit, I'm getting 3x squared minus 6x is greater than 0. I need to solve that now, so I'm just going to do a little bit of factorizing so I can take out 3x. So 3x multiplied by 1x minus 2 is greater than or equal to 0. So solving that, I get 3x is greater than 0, or equal to basically is how we're solving it. So x is equal to 0 divided by 3, so x is equal to 0. 1x minus 2 is equal to 0, because we're letting it equal because we need to find our roots where it actually crosses the x-axis, where it's equal. So x is equal to 2. And if I was to look at that on a coordinate graph, so let's just do a quick sketch of this. So I'd have the coordinates x is equal to 0, x is equal to 2. It's a positive because it's greater than 0, and it's a quadratic because it's 3x squared. So my quadratic looks something like that. And I want the values for where x are greater than 0. So that's above the x-axis. So I'm looking for this portion of the graph and this portion of the graph. So I'm looking for everywhere above the x-axis basically. So therefore my values for x are going to be x are greater than 2 and x less than 0. I can't accept any value between 0 and 2 because then that would end up being below 0. And that is question 4. Question 5a, you show by using an infinite geometric series that 0.18 can be written as 2 over 11. So you notice here with the 0.18, it has the two little decimals, the points above them. Basically what that means is that it's reoccurring. It's 18, 18, 18, 18, all the way to infinity basically. So it's a reoccurring decimal. And with this style of question, we want to basically break that up. So if we look at the first two parts of it, the 0.18, and we put that as its own decimal, so that's 0.18. And imagine then the next part to it, the next 18. So that's basically the same as going plus 0.0018. So I basically eliminated the part in red, so that's that. The green then is 0.0018. What about the next two then? So imagine the next 18. So I have 4 decimals accounted for, so plus 0.000018. So if I was to add those 3 values together, I would get 0.181818. And so on and so on. So that's basically how we're going to write our reoccurring decimals. So I'm using addition here. And if I was to put them as fractions, so again, you can just put these into the calculator and press equals, but that's the same as 18 over 100 plus 18 over, is it 4 zeros there? It would be 0, 0, and then the 18. So 1, 2, 3, 4. Then I would have 18 over 1, 2, 3, 4, 6 of them. 1, 2, 3, 4, 5, 6, which is a million basically. And again, so on and so on and so on. So you can see here that it's repeating itself. It's a series because it's addition, and then geometric because it's going up by the power. The multiplier. If I divide them, I get a common ratio, in other words. So here my first term in the ratio in the pattern would be 18 over 100. That would be my A. My ratio, what it's going up in, would be taking any two terms and dividing them by each other. And if I divide any two terms, I get 1 over 100. So in other words there, take any term, so take term 3 and divide it by the term that just comes before it, term 2. Again, you can take term 4 divided by term 3, term 2 divided by term 1. Then I'm going to my log tables on page 22, and I'm taking down the sum to infinity formula. And it's given as A over 1 minus R, because this recurring decimal goes on to infinity. And filling in the sum to infinity here, I get A, which is my first term, 18 over 100, divided by 1 minus the R, which is the common ratio, which is 1 over 100. And if you put that into your calculator now, you should get 2 over 111. So 2 over 11. So question 5b. So prove that Sn is equal to A times 1 minus R to the n all over 1 minus R. So we have the sum of our terms, and our first term is going to be A. Our second term, A R, so that's R to the power of 1, and our first term, R is to the power of 0. Our next term, A times R to the power of 2. Our next term, our fourth term, A times R to the power of 3. So you can see my power is going down. So on my fourth term, the power is to the power of 3. So when I get to my last term here, I'm writing it as plus A times R to the power of n minus 1. So that would be my last term. And in order to show that that is equal to A times 1 minus R to the n all over 1 minus R. And to do that, we're going to use proof by induction. And proof by induction is a 3-step process. We show it's true for n is equal to 1. We assume it's true for n is being equal to k. And then finally, we prove that it's true, or we show it's true for n is equal to k plus 1. So that's what we need to do. So our first step is to show true for n is equal to positive 1. So I'm basically going to sub that in to my formula. So S of 1 is equal to A times 1 minus R to the power of n. N is 1 in this case, all over 1 minus R. And that is giving me A times 1 minus R all over 1 minus R. 1 minus R will cancel out. So that's basically just leaving me with the sum of the first term equal to A. And that is true. We can see from our sequence at the top, our first term is A. So we've shown it's true for n is equal to 1. Now though, we want to come along and assume it's true for n is equal to positive k. So we want to show that it's true for n is equal to k. So I'm coming along now and I'm taking my sequence from up above, which is going to be A plus AR squared, and so on and so on and so on, until I get to A or to the n minus 1. Now n, I'm going to substitute in with a k, subtract 1. And I'm assuming that that is the same as A times 1 minus R to the power of n, which is now a k, all over 1 minus R. So I'm assuming that that is true. So now my third and final step is to prove through for n is equal to k plus 1. That's my final step now that I have to carry out. So basically what I'm going to do is, if you can kind of imagine it here, I'm going to keep all of these terms. These are all coming down. And all I'm doing then is adding on my next term. So I'm at term k and I'm now going to the next term k plus 1. So these are all coming down with me. So I have A plus AR squared. and so on and so on and so on, a or k subtract 1. But now what I'm doing is I'm subbing in k plus 1 where I had my n. So this will now become, my next term is going to become, let's just change the color here, plus a or k plus 1 subtract 1. So hopefully you can see that this k plus 1 here is being subbed in for the n, and then the minus 1 here is this minus 1. So just don't mix up the ones as you go through. And what I want that then to be equal to, I'm trying to show that that is equal to a times 1 minus r to the power of k plus 1 all over 1 minus r. So throughout this proof now, from here on in, I'm going to ignore the right hand side. That's what I want to show is true, but I'm basically just ignoring it now. So tidying it up, we've now assumed that this part, let's just box it off in green, that this portion, we've assumed that that is equal to a times 1 minus r to the power of k all over 1 minus r. Again, I'll just arrow it down, it's coming from here. That's our assumption from up above, so I'm using that assumption here in my proof. And I'm going to add on my additional part, a r to the k plus 1 subtract 1. And again, that's going to hopefully equal to the right hand side. My next step now is to hopefully see that this plus 1 and minus 1 can cancel out. So that's just leaving me then with a r to the power of k. So I have a times 1 minus r to the k all over 1 minus r plus a r to the power of k. I'm going to put that over 1, and I'm going to find my common denominator so I can add these two fractions together. So my common denominator here is going to be 1 minus r. So I'm going to keep my left-hand fraction as it is. It's already over my common denominator, so nothing to do there. But my right-hand fraction is now going to become a multiplied by r to the k times 1 minus r all over 1 minus r. And again, I'm trying to prove that that's equal to the right-hand side. Making it a single fraction now, I'll have a times 1 minus r to the power of k plus a r to the power of k times 1 minus r all over 1 minus r. I'm now going to multiply in the factors. So if I'm multiplying this a and multiplying this a r to the power of k into the second bracket, so I get a 1a minus a r to the power of k plus 1a r to the power of k minus a r to the power of k times r. What's common to all four terms? There's an a common to all four, so let's factorize out the a. Again, don't forget actually, that's over 1 minus r. So if I factorize out the a on the top, that's giving me a times 1 minus r to the k plus r to the k, or 1 r to the k, minus r to the k times r, all over 1 minus r. Look inside now, I have a minus rk and a plus rk, they can cancel off. Next step I'm going to focus in now on is this part here, this r to the power of 1. Using my log tables, I'm going to join in that r to the power of 1 with the r to the power of k. So that's the same as a times 1 minus r to the power of k plus 1. So r to the power of k times r is the same as r to the power of k plus 1. So that's just coming from my log tables. All over 1 minus r equals. And you can hopefully see that we are done, because what were we trying to prove? The aim here was to get it equal to this, which is a times 1 minus r to the k plus 1 all over 1 minus r. And you can see that I now have the same on the left and the right of the equals. So my conclusion is, so therefore it's true for n is equal to k plus 1. And why? Since true for n is equal to 1, we've proved true for n is equal to k plus 1, so therefore it must be true for any value for n. And that's our proof. Part C, hence or otherwise prove the sum to infinity of a geometric series can be written as a over 1 minus or. So not too much written work in this, it's more theory based. So what we're going to do here is we're going to use our knowledge of the sum formula, which is given in our log tables as a times 1 minus or to the power of n all over 1 minus or. Now if you think about that formula here, I'm just going to write it over here to the right as our rough work section. It's a times 1 minus or to the n all over 1 minus or. Now think to yourself what happens when the n changes here as part of our power. Now in our log tables, first of all, actually just to note, it says that the value of or is always a positive and is less than 1. So basically it means it's between 0 and 1. And if you put any number, any fraction or decimal between 0 and 1 to a power, it's always going to be positive first of all, and it's going to be greater than 0. So let's just assume, say for instance, our or here. So we're focusing in on this part here. That's what we're looking at. If we put our or, say to, let's keep it simple, 1 over 4 and our n as 2, that's giving us a 16th. So we can make that bigger and bigger and bigger. We can go 1 over a million if we wish and put it to the power of another million. Now that's going to be an extremely small value on our calculator. It's going to be 0 point with a load of zeros. But the one thing we know is that it's not going to give us 0. What it's known as, and the words we're using here, is that it tends towards 0. We're kind of looking into infinity here. We can pick any number off out in infinity, sub it in for n, but it's still going to give us a value extremely small, but never 0. So it's tending towards 0. And that's drawing our attention to our calculus section, which is looking at the limit as n approaches infinity. So we don't know what that value is. It's off out into infinity. So if we come back over here, so to our solution here, so we're looking at our formula here. So if we think about or to the power of n, imagine if we were to get to that value of 0, basically, we're subbing in 0 or to the power of an infinitely large value. And we put that over our 1 minus or, that's giving us a times 1 over 1 minus or. So what I've picked here is some extremely large number. So I'm going to the sum to infinity. And if I multiply a times 1, I get a over 1 minus or. So that's our formula for the sum to infinity given. So again, it's got to do with our limits here as the n approaches infinity. Question 6a. Find the derivative of y is equal to 3x plus sine x. Hopefully it shouldn't be too bad. So y is equal to 3x plus sine of x. The derivative of 3x is when you just drop the x, so that'll just give me 3. And from page 25 in our log tables, the derivative of sine becomes a positive cos x. So dy dx is equal to 3 plus cos x. B, differentiate cos inverse x over 4 with respect to x. So we have the function y is equal to cos inverse x over 4. So that's what we want to differentiate. In my log tables, I'm given cos inverse x over a, which is equal to minus 1 over the square root of a squared minus x squared. So that's in our log tables. So that's basically what I'm going to use here. And all I need to do is basically change the letters. So here I'm going to get dy dx is equal to, what's that going to give us? So it's going to give us a minus 1 on top of the fraction. All I need to do basically is change my value for a. Now the a is basically the number that's on the bottom of the fraction, the denominator. So my a is going to be just 4 squared minus the top, which is x squared. So my answer here is just basically negative 1 over the square root of 16 minus x squared. And that is part B complete. So again, all from the log tables. Part C, differentiate cos inverse 4 over x with respect to x. So I'm going to use the chain rule here to solve this. So using the chain rule, I'm going to break it up. So I'm going to let I'm going to use u as my letter. So I'm going to let u is equal to the 4 over x. So I'm taking that part out. So let u is equal to 4 over x. And I'm then going to take y as equal to the cos inverse of u. So I basically substituted in u for 4 over x. Differentiating both sides. So that gives me du dx is equal to, or actually before I differentiate it, let's actually turn it out of a fraction. Let's get it out of its fraction form. So that's the same as 4x to the negative 1. So that's coming from my log tables. And now I differentiate it and I get du dx is equal to reducing the power by 1. I get, and multiplying it down to the coefficient of the x, so minus 4x to the negative 2. So that's it differentiated. And if I want to turn it back now into fraction form, that will be minus 4 over positive x squared. Now coming over to the right hand side, I need to differentiate y is equal to cos inverse of u. So again, coming from my log tables, that's just going to leave me with, similar to part B, dy du is equal to minus 1 over my a, which is 1 squared, minus my x, which is u. Again, this is like putting the u over 1. That's what I'm doing here. And that's in the square root. And when I evaluate that, I just get negative 1 over 1 squared, which is 1 minus u squared. Okay, now I want to put them back together. So let me just make a bit of room here. So I'm now going to do dy dx. That's what I need to differentiate. And that's equal to du dx times dy du. So I need to just basically put it back together. So what's that going to give me? Dy dx is equal to du dx, which I have as minus 4 over x squared, times dy du, which is minus 1 over 1 minus u squared. Now I'm going to actually sub back in my value for u now in a second. But let's tidy it up a little bit. So if I can multiply these out, so top by top and bottom by bottom here, that's how I multiply fractions. So minus 4 by minus 1 is positive 4 over x squared times the square root of 1 minus u squared. So that's what I'm leaving myself with when I multiply the two fractions. Again, they haven't left us a lot of room here, have they? Bringing it up, subbing back in my value for u. So dy dx is equal to positive 4 all over x squared times the square root of 1 minus u, and u is 4 over x. That's what we substituted at the very start of the question over here. And that's an acceptable answer, but we'll just keep multiplying it out and simplifying it down a wee bit. So I can multiply out that bracket or square it out. So we get dy dx is equal to 4 over x squared times 1 minus 4 over x by 4 over x, well, top by top, bottom by bottom, which is giving me 16 over x squared. That's what I get when I work that out. Let's get a common denominator there for inside the square root. So dy dx is equal to 4 over x squared times x squared over x squared, if I get my common denominator. So 1 over 1, or x squared over x squared, minus 16 over x squared. We could write it like that. Let's go a little bit further now. What else could we do? Well, let's make it a single fraction first of all. So dy dx is equal to 4 over x squared times x squared minus 16 all over x squared. That's another way we could write it. Let's just make our square root a little bit neater. And what next? We could perhaps, or actually what we could do is we could open up that square root and put it to the top and the bottom again, coming from our log table. So this is going to be the square root of x squared minus 16 over the square root of x squared. And the square root of x squared, which is x by x, just cancels to be x. So dy dx is equal to 4 over x squared multiplied by the square root of x squared minus 16 over x. I'm then going to cancel off this x with one of these two, which will leave me then with dy dx is equal to 4 over x times x squared minus 16. Okay, I think I'll leave it there. That's as far as I can go. So hopefully that makes a little bit of sense. Bit of work in that one. Part D, if y is equal to cos x times sin x, write dy dx in the form cos n of x. So we're basically looking for some factor there in front of the x, isn't that it? So how would that look? So we have y is equal to cos x times sine of x. That's what we're given. Let's use the product rule because we're multiplying here. So the product rule from my logs on page 25, I would have u as cos x, and when I differentiate it, I have du dx. Again, from the log tables, cos becomes minus sin x. Then I'm going to break out my v. My v is my sin x, and dv dx is going to give me cos x. So when I differentiate sin x, I get cos x. The rule then for the product rule is given by dy dx is equal to u times dv dx plus v times du dx. Again, that's all from the log tables there. So filling that in, I have dy dx is equal to u, which is cos x, multiplied by dv dx, which is cos x again, plus v, which is sin x, times du dx, which is minus sin x. And cos x by cos x is cos x squared, or cos squared x. We put the square on the cos, not on the x, just the way it's written. And positive by negative would give me a negative here. And sine by sine, again, would be sine squared x. Again, the squared goes on the sine, not on the angle. And you can hopefully notice here, actually, from page 14 in the log tables. It tells us in the log tables cos squared a minus sine squared a is the same as cos 2a, or cos 2x. So therefore, dy dx is equal to cos 2x. Again, as I said, that's coming from the log tables on page 14. And that's the end of question 6. So question 7, we're looking at the image here, and part A is asking us to write down the length, the breadth and the height of the box in terms of x. So first of all, let's write down our length. So our L is going to be represented as the full length of the box, which is 20. And then we're folding up the two corner ends, which are both x and x. We're basically subtracting x from 20 twice. So 20 minus x, that's both ends. So that's the same as 20 minus 2x. So that's the length of the box. The breadth of the box, or the width of the box, we're going in the opposite direction this time. So we have 12 as the width. We're going to fold over the two ends, which are x and x. So that's leaving us with 12 minus x, which is 12 minus 2x. And then the height of the box is the corners basically that we're folding up, and the height of the box is represented by x. So that's our length, width and height of the box. Nothing too difficult there, hopefully. Looking at part B then, it is asking us to hence show that the volume of the box can be represented by this function, the volume V. So we have our formula for volume as length by width by height. In this case, width is the breadth. So we'll just change that around, length by breadth by height. And if we fill that in, our length is 20 minus 2x. our breadth as 12 minus 2x, and our height of x. So we basically just need to multiply this in. I'm going to start from the back. I'm going to multiply in that x first of all. So that's giving me 20 minus 2x multiplied by 12 by x, which is 12x, minus 2x by x is minus 2x squared. So that's what I now need to multiply out. So first term by second bracket, so 20 multiplied by 12x minus 2x squared, and then the second term minus 2x by my second bracket again. Multiplying that in now, that's going to give me 20 multiplied by 12, which is 240x. 20 multiplied by minus 2x squared is minus 40x squared. Minus 2x by 12x is minus 24x squared. And then finally, minus 2x by minus 2x squared is giving me a positive 4x cubed. Rearranging that to the degree of the highest value first, so that's my 4x cubed. I'm then going to put the minus 40x squared with the minus 24x squared, which is giving me a negative 64x squared. And then finally, my positive 240x. And that's what they wanted in the top of the question here. Show that the volume can be written as 4x cubed minus 64x squared plus 240x. And that's what we have. Looking now at part C to that question. Use calculus to find, correct the three significant figures, the value of x, which gives the maximum volume of the box. So as soon as we see the keyword here, which is maximum, we know we need to differentiate and let it equal to 0, because when we differentiate, we're finding the slope, and the maximum is going to be when the slope is equal to 0. So the volume of our box is 4x cubed minus 64x plus 240x, and I'm going to differentiate that, so dv dx is equal to 12x squared minus that's a squared, minus 64x squared minus 128x plus 240. That's my constant, and we are looking for the maximum. So that basically means when I said our slope is equal to 0. So dv dx is equal to 0. So rewriting it, we have 12x squared. Sorry, I missed my squared there as well. 12x squared minus 128x plus 240 is equal to 0. Now I can spot there that I can divide across by 4 just to make it a wee bit easier on us. So dividing across by 4, you don't have to, but it might make it easier. 3x squared minus 32x plus 60 is equal to 0. Now the key with the question there is it says give it to three significant figures, so that means our solutions are going to be decimals. So I'm going to go straight for our minus b formula here from our log tables, which is written as x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And just writing down what we know, our a is the value in front of the x squared, which is 3. The b is the value in front of the x, which is minus 32. And the c is my constant, which is 60. So that's just my piece of information there. So let's do it out now. So filling it in, I have x is equal to minus b, which is minus 32, plus or minus the square root of b squared minus 32 squared, minus 4a, which is 3, and c, which is 60, all over 2 times a, and a is 3. So x is equal to 32, because minus minus becomes plus. And working this out on our calculator, just make sure that you put the minus 32 into a bracket, and I'm getting 304 all over 6. And if we do that out for the plus and the minus, we have x is equal to 32 plus the square root of 304 over 6, and x is equal to 32 minus the square root of 304 over 6. So what are we getting? X is equal to 8.239 for my first value for x, and my second value for x I'm getting 2.427. Now there can only be one value for x, because it says up the top here find the value of x, we need to find out basically which one of these is going to give us the maximum volume. So in order to show if it's maximum or minimum, we need to find our second derivative. So that's what we need to do now. So I know that dv dx is equal to 12x squared minus 128x plus 240. That's what I have at the start of the question. And I'm going to differentiate that again. So my second derivative is going to be 24x minus 128. So that's my second derivative. And now what I do is I'm going to sub in my values for x. And if we get a positive value for x, or greater than 0, basically, it's our minimum, and less than 0, it's going to be our maximum. So that's basically what we now have to do. So first of all, I'm running out of space here, but let x equals my first value, which was 8.239. And I'm subbing that into my second derivative, which is 24 times 8.239 minus 128. And when I work that out on my calculator, I'm getting 69.736. So that's my first value. That is greater than 0. So therefore, this must be my minimum. But let's do out our second one just to be sure we haven't made a mistake somewhere through our question. Let x equals to my other value, which was, what was my other value? 2.427. So this is my second value for x. So subbing it in, 24 multiplied by 2.427 minus 128. And when I work that out, I'm getting minus 69.752. And this is less than 0. So therefore, this must be my maximum. So what does that basically conclude? That tells us then that it's asking us to find the value for x, which gives us a maximum. So therefore, the value of x that is a maximum is the 2.427. And it wants us to give it to 3 significant figures. So therefore, x is equal to 2.43. That's my 3 significant figures. Don't mix our significant figures up with our decimals. So 2.43 centimeters. Looking now at part D, use the value of x from part C, find the maximum volume of the box, correct to 3 decimal places, or 3 significant figures again, actually. So the volume of the box we have from part B. So our volume was written as 4x cubed minus 64x squared plus 240x. And all we're doing here is we're basically subbing in our value of x. And I'm going 4 bracket something cubed minus 64 something squared plus 240 times something. And I'm subbing in now my value for x from part C, which was 2.43. And when I work that out on my calculator, I'm getting a volume of 262.682. And again, the question said the 3 significant figures. So our volume here was 263 centimeters cubed. And once again, don't mix our significant figures up with our decimals. So there's 3 digits in our answer, which is 263 when we round it. Okay, and our final part of this question is part E. Students wish to plot the graph of the function. They wonder what domain they should use. Write down the domain the students should use in the form A is to B, where A and B are elements of the real numbers. And explain why you chose them. So my explanation here is basically going to be mathematics, in other words. So let's look at the rectangular sheet of cardboard again. We have our length as 20 minus 2x. And we have our width or our breadth as 12 minus 2x. So they're coming from part A and B. And if you think about it, we first of all have to keep x greater than 0. Because if you think about putting in a negative number for x, so let's just try one, we would have something like 12 minus 2. And if I put in a minus 1, I would get a positive 1. So 12 plus 2 would be 14. But the width of this box can't be basically greater than this 12. It can't be above the 12, because if we scroll back up to the top of the question here, the total width of the cardboard is 12. So obviously I can't make that into a 14. So that's the first value of x. We can't go above 0. Or sorry, we can't go below 0. So that's my first input for my domain. And then if we look at the greatest value then for x, so if we have our width of our box, so our width of our box is 12 minus 2x. And that has to be greater than 0, we said. So I'm just going to solve this basically. So if I take away 12 from both sides, now divide across by minus 2. And when we divide with a minus with inequalities, it changes the direction of my inequality. So I'm getting x less than positive 6 there. What happens if we carry out the same experiment for the length of the box, 20 minus 2x? And again, it has to be greater than 0. I move over to 20 or subtract it from both sides. I get negative 2x is greater than minus 20. Divide both sides by a negative 2, makes that a 10. My inequality sign again changes. Now, I can't accept both, and I will explain why. I can't accept the 10. I do accept the 6. Because once again, we have to pick one value for x. And if we pick our value of x as, say, the 10, and I come back to this one here, if I was to sub in 10 as x, I would get 12 minus 20, which is a negative solution. And I can't have a negative length of a side of a cardboard box. So that's why the maximum value for x must be the 6. So therefore, my inequality is going to be x less than 6, but greater than 0. And there's my final answer. Now let's look at part F, where it wants us to sketch this function. So use suitable scales for the axes, draw the function for volume in the domain that we've just set of 0 to 6. So let's first of all mark out my x-axis. So we're going up to 6. So we'll go 1, 2, 3, 4, 5, 6, and we'll go to 7 just to keep it simple. And what are we going up to? We got a maximum volume, I think, of about 263 from part D. So we need to go up, maybe let's go up in 50s just to keep it simple. So we have a 50, 100, 150, 200, 250, and 300. So that's my volume of the box here. And let's look at a little table here. Let's look at putting in a value for x and what value we get out for y, for volume. So when I put in, well, what have we got? We have from 0 to 6 is the domain we set. So 0, 1, 2, 3, 4, 5, and 6. So my function is 4x cubed minus 64x squared plus 240x. So I'm subbing in my values for x into that. So when I put in 0, I get an output of 0. So my coordinate there is 0, 0. So we'll plot that. The next point is subbing in 1. When I sub in 1 to the function, I get 180. So that's 180. So again, I'll plot that. That goes up around here. The next one is 2. When I put in 2, I get 256. So the coordinate there is 2, 256. 256 to 2. Subbing in 3, I get 252. So it's starting to come back down now a bit. My next one, when I put in 4, I get 192. So 4, 192 is my couple. And that is about here. Subbing in 5, I'm getting 100 as my output. So 5, 100. And we'll plot that around here. And finally, I sub in 6. And when I sub in 6, I get 0 again. So it's coming back down to my x-axis. And that's my quadratic. So again, a nice freehand curve, kind of difficult when I'm on the computer here, but it looks something like that. So that's my function. And you can see it doesn't ask us here, but it did ask us in part D to find the maximum volume of the box, and that was around here. So you can see here that it's slightly above the 250, which would be around the 263. So that's just verifying my answer to part D. It didn't ask us to do it, but hopefully you can see that from the image. And that is the end of question 7. Question 8a. A depth charge is an anti-submarine warfare weapon that was used extensively during the Second World War. A depth charge testing facility collects data on how far the shockwave of an explosion travels in each second after the explosion. They collect the following observations. So you have the time, 1, 2, 3, 4, and then you have the distance traveled in the previous second, and it's measured in meters. So assuming that the distance traveled in the previous seconds follows a geometric sequence, find the common ratio R. So our geometric sequence is basically going up by a multiplier. And in order to find what that multiplier is, or that ratio, all you have to do is divide any term by the term which precedes it. So in other words, you're dividing, say for instance, term n, and you're dividing it by term n minus 1, so the term just before it. So just pick any term. I'm going to pick, say, term 2, and I'm going to divide it then by term 1, which would be 518.4 divided by 777.6, which is coming out as 2/3. Again, it doesn't matter which two terms you do, they have to be consecutive though. Part 2, find the total distance travelled by the wave in the first 5 seconds. So they're looking for the total distance travelled in the first 5 seconds. It's a geometric series. So I'm going to my log tables on page 22, taking down the sum of the terms, which is given by a times 1 minus r to the power of n over 1 minus r. Just writing down everything we know here. A stands for the first term, which is 777.6. N is the first 5 seconds, and r is the common ratio, which is 2/3. So that's my little bit of work that I need to use. And filling it into my formula now, I have the sum of the first 5 terms, so S5 is equal to A times, so 777.6 times 1 minus r is 2/3, and that is to the power of n, which is to the power of 5. And that's all over 1 minus r, 1 minus 2/3. And when I put that into the calculator, I'm getting a total of 2025.6 meters. If you want to go kilometers, I don't think it says, but we can work to kilometers if you wish. 2 kilometers, 0.0256. So divide by 1,000 there to get it into kilometers, but I don't think it asks. The next part to that question, part 3, in which second does the wave travel less than 100 meters for the first time? So you're looking for the term number here. And again, we're working off page 22 in our log tables, and we're looking for Tn as a geometric series this time. So A multiplied by R to the n minus 1. So that's the formula I'm using here. And I need to have the term number less than 100. So travels less than 100 meters. So I'm going less than 100. Filling in everything, my A is the first term, 777.6. My R is 2/3, and my n minus 1, well, n is what I'm trying to solve for, but less than 100. I'm going to divide across by 777.6, so that's 2/3, n minus 1 less than 100 over 777.6. If I simplify 100 divided by 777.6, I get 0.1286. So that's leaving me with 2/3 to the power of n minus 1 less than 0.1286. Next thing I'm going to do is, in order to solve for the power, I'm going to use my rules of logs. So page 21 in my log tables, I'm using the a to the power of x is equal to y is the same as log a to y equals x. So I'm using this top right hand corner of page 21 in the log tables. And filling that in now, I have, so I'm looking for log to the base a, which is my 2 over 3, 0.286, and that is equal to x, and x is my power, which is n minus 1. When I work out my log, I get 5.0585 is equal to n minus 1. So just to go back on that if you need it, so if you follow through here, the a is the 2 over 3, the x is my n minus 1. So that's where all that information is coming from. And then if we color code it again, there's my n minus 1, my a is here. That's where those terms are coming from. And my y then is the equal to 0.1286, which is here. So maybe the colors help to follow your way through it. And my final step is I'm going to then move over the -1, so add 1 to both sides, which is 5.0585 plus 1 is equal to n. So n is equal to 6.0585. Now we need to linear a second, so therefore my solution here would be n is equal to 7 seconds. So don't round down, because if we sub in 6, it would not give us a distance of less than 100 meters. We need to round up to 7 seconds. Even though I know it's 6.05, we're commonly used to rounding down, but not in this case in a practical word problem question. Okay, so that is A part 1, 2, and 3. Now scrolling down to the next page for part B. And it's saying that depth charges are also used to check the presence of submarines. Water resistance is greater than air resistance, with the distance travelled in the previous second following a geometric distribution with a common ratio of 1/9. Complete the following table. So basically what's happening here is that we need to multiply each term by 1/9. That's basically how the table is continuing. So in order to get in here, we go 729 multiplied by 1/9. So that's basically our common ratio. It's been multiplied by 1/9. Now you could also just divide 729 by 9 if you want to use division, but multiply by the fraction or divide by the number. So that's giving me 81. For in here, it would be 81 divided by 9 or 81 multiplied by 1/9, which would give me 9. Next box would be 9 divided by 9, which is 1. In the fifth one then, it'd be 1 multiplied by 1/9 or divided by 9, which is 1/9. And then finally, in second 6, it would be 1/81. Part C. The lake where the depth tests are taking place is home to particularly fast-growing lily pads, which double in size each day. The surface area of the lily pads is initially 5 meters squared. Find the area covered by lily pads after the nth day. Okay, so on day, let's call it day 0. So today, the surface area of the lily pads is 5 meters squared. So that's what we have right now on day 0. It's then telling us that it is doubling each day. So today it's 5, the next day it's 10, the next day it's 20, the next day it's 40, the next day it's 80. So it's doubling as we go. How would that look? So that basically means our power is changing. So if it's doubling, it's to 2 to the power of some term. Let's call it n for n days. And we'd need to then multiply that by 5 because it's starting off at 5. So 5 times 2 to the power of n. So 2 to the power of 2 would be 4. 4 by 5 would be 20. Yeah, so wouldn't that work? So if we were to test it here, so you sub in 2, you would get 2 2s are 4. 4 by 5 is 20. Yeah, okay. So 5 multiplied by 2 to the power of n. That would be our area of lily pads after the nth day. Looking now at part 2 to that question, it takes 30 days for the lily pads to cover all of the lake. Find how long it takes for the lily pads to cover exactly half of the lake. So let's first of all find the total area of the lake. So we need to find the total area covered by the lily pads, and we know that it takes 30 days to cover the lake, so that would be 5 times 2 to the power of 30, and that is giving us a total area of 536870920, so quite a very large number there. And it's then telling us that it wants to find how long it takes to cover half the lake, so I'm going to divide that by 2 to get the area that we're basically concerned with, which is 2684354,560. So that's the area of our lake in meters squared, and we want to basically find out how long it takes to get to that stage. So I'm taking my formula, which is 5n squared, and I want that to equal 2684354,560, the area of my half lake basically. I'm going to divide across by 5, so n squared, sorry, that's 2n, isn't it? Not n squared, my fault. So 5 times 2n, but still dividing across by 5 will give me, give me 1 second to write it out. So 2 to the power of n is equal to 536870912. I'm going to again use my logs tables on page 21, top right hand corner here, and it says a to the power of x is equal to y is the same as log a to the y is equal to x. And filling that in now, I have my log. Now I need my a. The a is the value to the x, which is 2. My y is the value it's equal to, which is 536870912. And when I work that out in my calculator, I'm getting 29 days. So here it's taking 29 days to get to half the lake to be covered by the lily pads. And that kind of makes sense because it tells us it doubles every day. So if it's half full on that day, then by the next day, it's going to be basically double. So we could have just kind of taken 1 away from the 30. Perhaps that was the easier way of doing it, but we've used mathematics to get there. And that's the solution then to question 8. Question 9. So when testing rockets, NASA uses an aircraft to carry the rocket to a set height. Before dropping the rocket into freefall, its thrusters are then engaged and the rocket begins to gain height. Wiki, a rocket scientist, models that the height of the rocket in kilometers is given by this function. So S of t is finding us the height. And it's then saying that where a is a constant, where a is between 0 and 60, and t is the time in seconds after the launch. Part A then is asking us to use calculus to show that the speed of the rocket after t seconds can be displayed as the following. So you can see here it's getting us to find ds dt, so it's getting us to use calculus here, differentiation. So we basically just need to differentiate our function for height, s of t. So that's our first thing we need to do here. So to differentiate this function, to get rid of the square root first of all, and I'm going to put it to the power of a half. So I'm just taking out my original function and I'm rewriting it to the power of a half. I'm now going to differentiate this, and to differentiate this I'm going to use my chain rule. So I'm going to let what's inside the bracket equals to u. So I'm taking out the a over t plus t over a, and I'm letting that equal to a. So my new function in terms of u is going to be s of u is equal to u to the power of 1/2. So I've substituted in my u. If I differentiate that, so that's going to give me ds du, and differentiating u to the power of a half would bring down the power, gives me a half, times u, and take 1 away from my power, which would give me negative a half. I'm just going to tidy that up a little bit then. So that is the same as ds du is equal to 1/2 times 1 over u to the power of a positive a half. So I just don't want that negative a half really. I'm then going to turn that back into the square root. So it's a half times 1 over the square root of u. And if I multiply top by top and bottom by bottom there, I'm getting ds du is equal to 1 over 2 root u. Okay, next thing I'm going to look at is I'm going to look then at my u and differentiate it. So I'm coming back over and I'm taking my u, which I've substituted in for a over t plus t over a. And I just want to differentiate that again, bring up those powers, the fractions, get rid of the fractions. So I'm rewriting it as a times t to the power of -1 because this t is to the power of 1. And then I'm just going to separate out the second fraction. It's 1 over a times t. So I don't need to bring up that a because it's 1 over a. I'm differentiating the t. So now if I differentiate this, I have du dt is equal to minus 1a times t to the power of -2 when I take away the 1 from the power. And then when I differentiate 1 over at, that just gives me plus 1 over a, because the t is to the power of 1 and reduce 1 from it, it becomes t to the power of 0. So rewriting that, I have du dt is equal to minus 1a times 1 over t to the power of positive 2. So I'm turning that t to the -2 into my fraction, and then that's plus 1 over a. And that's the same as du dt is equal to minus 1a or minus a over t squared plus 1 over a. So my next part now is to put this all back together. So I'm trying to find ds dt, and ds dt is found by multiplying ds du times my du dt. And filling that in, I have my ds du, which is 1 over 2 root u. And I'm going to substitute back in my original value for u now in a second. But that's 1 over 2 root u times my du dt. And my du dt is this value here. So that's giving me, multiply it by minus 1a over t squared plus 1 over a. And if I substitute back in my value for u, as I said, so it's going to be 1 over 2 times a over t plus t over a. And that's all going to be multiplied by minus 1a over t squared plus 1 over a. And I'm just going to put that now as a fraction over 1, and I'm going to multiply top by top and bottom by bottom. So ds dt is equal to minus a or minus 1a over t squared plus 1 over a all over 2 times the square root of a over t plus t over a. And that's part 1. That's now the same as this. I think I just need to rearrange the top there to give me 1a minus a over t squared, but just change that around yourself. So looking at part 2. Given that the height of the rocket 30 seconds after launch is 2.7 kilometers, show that the value of a corrected 3 decimal places is 4.196. So our function s of t, or height in other words, is given as the square root of a over t plus t over a. That's what we're given. And it wants us to now show, given that the height of the rocket 30 seconds after launch is 2.7, so I'm substituting 2.7 in for my st, my height, and I'm letting that equal then to the square root of a over t, which is 30 seconds, plus t, which is 30 over a. I'm going to square both sides then to get rid of the square root. So if I square the right hand side, I must square the left hand side. So that's giving me 7.29 is equal to a over 30 plus 30 over a. I'm then going to get rid of those fractions by getting a common denominator, and my common denominator here is 30a. Just put the 7.21 over or 7.29 over 1 to have three fractions. So multiplying across now by my common denominator is giving me 7.29 by 30a is 218.7a. When I multiply the a over 30 by the 30a, that's giving me a squared over 30a. And then the 30 over a, I just need to multiply it by the 30, which is 900 over 30a, my common denominator. I now have my common denominator and I have an equation. These are equal to each other, so I can now just basically drop the denominators. So therefore I have 218.7a is equal to a squared plus 90. Or 900. Rearranging, moving everything to the right hand side, it's the same as a squared minus 218.7a plus 900 is equal to 0. I'm asked now to solve for a, so I'm going to use my minus b formula. So the value of my a is 1, my b is minus 218.7, and my c is 900. And my minus b formula is going to solve for a, so a is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Now just watch here, this a isn't 1, that's like the formula in the log tables, it's x is equal to, but I'm not finding x, I'm solving for a this time. And subbing in my values, I have the value of a is equal to minus 218.7 plus or minus the square root of b squared minus 4 times a times my c. And that then is all over 2a, which is 2 times 1. And when I put that into my calculator, I'm getting a as 4.1957 and a is equal to 214.504. Now we can't take both. If you scroll back up to the top of the question here, it tells us just above a part 1, it says where a is a constant and a is between 0 and 60. So the question says that a can only be between 0 and 60. So therefore my value for a is going to be the 4.1957. I ignore the 214. So a is equal to 4.1957, and this part of the question, part 2, said to give it to 3 decimal points, which is 4.196. And that is now part 2 complete. Looking now at part 3, the local residents wish to know how close to the ground the rocket will fly. The minimum height occurs at the only turning point where t is positive. Calculates the time after launch that the minimum height occurs, corrected 3 decimal points. So our key phrase here is turning point. And a turning point on a curve happens when the slope is 0. So that's what a turning point is. And the slope, as we know it, is dy dx, differentiation. So we're basically letting our first derivative equal to 0. That's how we find our turning points. And we have that done in part 1. The derivative is given as 1 over a minus a over t squared, all divided by 2 times the square root of a over t plus t over a. That's given to me at the start of the question. And that's the derivative, so I'm letting that equal to 0. I'm now going to let my a equals my 4.196 that we found earlier. So subbing that in, I have 1 over 4.196 minus a, which is 4.196 over t squared, all divided by 2 times the square root of 4.196 over t plus t over 4.196. So a lot of subbing in there. Again, this is all equal to 0. Put that 0 as a fraction, 0 over 1, and cross multiply. So hopefully you can see here what's going to happen. So when I multiply the top of the first fraction by the 1 on the second fraction, that's giving me 1 over 4.196 minus 4.196 over t squared is equal to, now it's 0 multiplied by all of this, and 0 times anything is just 0. So that's leaving me with equal to 0. And you can see here, this is the only fraction with a t in it. So I'm going to isolate that fraction. So I'm basically going to pick up this, move it over to equals, and become a plus. Or just add 4.196 over t squared to both sides. So I have 1 over 4.196 is equal to a positive 4.196 over t squared. I'm going to use my knowledge of cross multiplication again. So I have 1 multiplied by t squared is 1t squared. And 4.196 by 4.196 is giving me 17.6064. And I want to get t on its own as t squared. So I get the square root of both sides. So the square root of 17.6064. And that's giving me a time of 4.196 seconds. The next part of that question, IV, says to find the minimum height of the rocket correct to 1 decimal point. Now, the height of the rocket, again, given at the very start of the question, is given by the function s of t, which is equal to the square root of a over t plus t over a. So that's the height of the rocket. And again, I know the value of my a, so I'm subbing that in. So it's the square root of 4.196 over t plus t over 4.196. And when does the maximum height happen? Well, we've got that just in part 3 because that's our turning point. So the maximum height happens when t is equal to 4.196. It's this figure here that we just found up above. So I'm basically just going to sub that in now for the value of my t. So that is giving me s of t is equal to the square root of 4.196 over t plus t over 4.196. And I'm subbing in my value for t, which is 4.196. 4.196. Now 4.196 divided by 4.196 is just 1. So s of t is equal to the square root of 1 plus 1, which is giving me the square root of 2. And the question wants it to 1 decimal point, and that is 1.4 kilometers. And that's the maximum height reached by the rocket. Okay, and the last part, part B. The fuel tank on the rocket is in a cylindrical shape. From a sensor fitted inside the tank, we can determine that the rate of change, so this question is talking about rate of change, of the fuel tank dH dt is 16 over pi meters per second. Find the rate of change of the volume of the tank in terms of ore. So the volume of a tank in this part of the question is telling us it's a cylinder. So the volume of a cylinder, we know from our log tables, is pi r squared h. And if I find the derivative of that, dv dh, so because the part that's changing in this cylinder is the height, so it's the rate of change with respect to the height. And differentiating, I get h multiplied down the power, so that just gives me 1 pi r squared, and I knock off the h because h is to the power of 1, 1 take away 1 is 0. So that's dv dh found. The question then tells us that we have dH dt. They give us that in the question, which is 16 over pi. That's coming from here. So that's another thing we have. And What we want to find though in this question is the rate of change of the volume of the tank in terms of ore. So we're basically looking for the rate of change, which is going to be dV dt, as the volume changes with respect to time. That's basically what we want, which is the same as dV dt is equal to dV dH times dH dt. And we have both of those pieces of information. So we can now solve that. So dV dt is equal to my dV dH, which is pi r squared, times my dH dt, which is 16 pi. And multiplying those out, this is the same as over 1, so top by top, bottom by bottom. That's getting dV dt is equal to 16 times pi r squared all over pi. And the pi's will divide into each other to give me 1. So that means that dV dt is equal to 16 r squared. Question 10a, January the 1st will be Connor's 21st birthday. On his 25th birthday, he will be able to cash in an investment which will pay out €20,000. Part 1, find the present value of this future payment of €20,000 in 4 years' time, correct to the nearest euro, assuming the annual interest rate is 2.5%. So from our log tables, we know that the compound interest formula is F equals P times 1 plus I to the power of T. F meaning final or future, P meaning the present sum of money or the principal. So if we manipulate this formula to get the present value, because that's what we're asked to find here, find the present value, P, if I divide across by 1 plus I to the power of T. So that's all I've done. I've just divided across by 1 plus I to the power of T, and that'll help us to find the present value. If we come over now and we sub in what we know, so the present value is going to equal F, which is the future amount, which is €20,000, over 1 plus I is 2.5%, divide 2.5% by 100, turns it into a decimal 0.025. So that's 1 plus 0.025 to the power of 4 years, I think it is, isn't it? Yeah, it would be. So 25th birthday to the 21st birthday, 25 take away 21 is 4 years. So present value is equal to 20,000 all over 1.025 to the power of 4, which is giving me a present value of about €18,119.01. Does it say to the nearest euro? It does say to the nearest euro here. So our present value is €18,119. Part 2, Connor decides to consider what he should do with the money when he receives it. He decides that he will try to purchase a house at the age of 30. He plans to invest his €20,000 in the stock market for 5 years, withdrawing it on his 30th birthday. He hopes that the investment will increase by 5% per annum, which is per year. If the investment achieves the growth rate of 5% per annum, what will the investment be worth at the end of 5 years? So text heavy there really, but basically it's just asking us to find the future value of the €20,000 in 5 years' time. That's basically all that question is asking us to do. So it's the same formula once again. This time we are trying to find the future value. The present value is now the €20,000 on his 25th birthday. And he's putting it in at an interest rate of 5% this time. So dividing 5% by 100 is 0.05. So that's 1 plus 0.05, which is 1.05 to the power of 5 this time, because it's his 30th birthday. Take away his 25th birthday gives me 5 years. And typing that in my calculator, I'm getting €25,525.63. And once again, the question said to the nearest euro, and to the nearest euro there would be a future value of €25,526. So his €20,000 on his birthday, his 25th birthday, will be worth €25,526 on his 30th birthday. Part B. Connor decides that when he turns 25 years old, he will start saving €500 per month, lodging the savings on his first day of each month. He will continue his regular savings until his 30th birthday. He will not make an allotment on his day of his birthday. His bank will offer an annual rate of interest on his regular savings of 2.5%. So, part 1. Find correct to 4 significant figures, the monthly interest rate as a percentage that is equivalent to an annual rate of 2.5%. Okay, so these are equivalent interest rates. So let's see what we have. We have the yearly rate, which is 2.5%, isn't it? Isn't that what we're given in the question? So we have our yearly rate, which is 2.5%, and we're basically now trying to find out what is the equivalent monthly rate. What is the monthly percentage rate? And basically with this style of question, we're looking again at our compound interest formula, but we're only looking at the 1 plus I to the power of t portion of it. We're not concerned about what the value of p and f are. We're only looking at the 1 plus I to the power of t. And if we fill that in for the year, it would be 1.025. That's the interest rate per year. And the power there would be to the power of 1 because it's 1 year. But coming over to the equivalent monthly rate, it's 1 plus I. I is what you're trying to solve for here. But the power would be 12 because there'd be 12 installments within 1 year. Now to get rid of that power of a 12, we either get the 12th root of it or we multiply it by 1 over 12 because 12 multiplied by 1 over 12 is 1. And if I do that to the right hand side, I'm going to have to do it to the left hand side. So I need to multiply the left hand side by 1 over 12. So that's giving me 1.025 to the power of 1 over 12 is equal to 1 plus I to the power of 1. Anything to the power of 1 is just itself, so I'm leaving out the bracket now, so that's 1 plus I. And 1.025 to the power of a 12th is 1.0020598. I'm then going to subtract 1 from both sides because I'm trying to solve for I here now. So moving over that 1.0020598 subtract 1 is equal to I. I is equal to 0.0020598. And we want to turn that into a percentage. So multiplying it by 100 to turn it into a percentage, moving my decimal point 2 places. So my interest rate there would be 0.20598. And the question wanted to, how many significant figures did it say? 4, wasn't it? So that would be 0.2060%. That would be my interest rate here. So 0.2060%. So part 2 to that question is asking us to find to the nearest euro the value of his savings after 5 years. So we kind of need to go back to the previous page here, part B, part 1. It's telling us that Connor is putting in €500 per month here. That's what's happening. And he's putting €500 in, so we'll just say our savings, and he's putting €500 in at an interest rate of our 0.2060, what we've just basically found out. So that is giving us 500 multiplied by 1.002060, and he's putting it in for what did it say, when he turns 25 until he hits 30. So that's 30 years minus the 25 years, which is 5 years, and it's per month. So we're going to multiply that by 12, which is giving us 60 months. And it says at the start of part B, he will be regularly saving and he'll be lodging it on the first day of each month. So that's why he'll be putting it in for 60 installments here. And then next month, he'll put in another €500 and it'll stay in there for 59 months because it's a month down the line. And he's going to keep doing that. But the question says that he's not putting in €100 on his birthday. So we have to go basically a month before his birthday, which will be €500, lodge that, the interest rate, but it'll only be in there for 1 month. We don't have anything to the power of 0 because he's not putting it in on the last day, that day of his birthday. So it's important that we kind of go back to B there and read that it's been put in at the start of the month and it's not going in at the last day. So that's our sequence that we're setting up. And from that now, we can hopefully see that we can start seeing that it's a geometric series. And I'm just going to rearrange Connor's savings in ascending order. So I'm going to go 500, 1.002060 to the power of 1. I'm just changing the order here basically. Nothing wrong with that. It's still the same sequence. 500, 1.002060 to the power of 59, and then plus the 500 to the interest rate to the power of 60. So it's the same thing. I'm just going to write down what I know now. I know that the first term, A, is equal to 500 times 1.002060. I have my OR, which is the common ratio, what it's going up in, and it's basically just going up by the interest rate, 1.002060. That's what it's going up by. And if you want to find your common ratio, just divide say term 2 by term 1, or term 60 by term 59, and the 500s will cancel out there. And then I'm going to my log tables and I'm taking down my sum of the terms formula, which is A times 1 minus R to the power of n over 1 minus R. And I'm doing it for S60, 60 months, A being 500 times 1.002060. And then I'm multiplying that by 1 minus R. R is 1.002060. And that's to the power of n, which is 60 months. That then is all over 1 minus R, which is 1 minus 1.002060. So a lot of decimal points here. We just have to be very careful as we fill in the formula. I'm getting then a total value of 31,963 euro 0.599. And the question says to the nearest euro, so that's giving me 31,964 euro. And that's the value of his savings in 5 years' time. The final part of this question, part C, let's scroll down and have a look at that. Connor thinks that when he turns 30 years old, the average house price will be 500,000 euro. He will use his returns from the stock market and his savings as a deposit for the house. The bank will loan him the remainder with an annual percentage rate of 2.5%. Connor will pay the loan back over 25 years, making regular monthly payments starting 1 month after he takes out the loan. Calculate, correct to 2 decimal points, the amount of each regular payment. So these are the regular payments basically as he pays back the mortgage. So let's see what Connor has. So Connor has his savings first of all. And his savings are 25,526 euro. So we've got that figure from part 2 of A. So that was Connor's savings. Then we're looking at Connor's stocks, and that's from part 2, B part 2, which is his investments of 31,964 euro. So how much is Connor altogether? He has 57,490 euro basically towards his deposit. So that's how much funds Connor has on his 30th birthday. Connor needs a mortgage of 500,000 euros. So let's kind of do a little bit of work with that. So his mortgage balance basically is what we need. So he's starting off with a loan of 500,000. He's going to take off the 57,490 that he already has. So Connor needs a mortgage of 442,510, 442,510 euro. Now, it's telling us that in the question that the bank will loan Connor at an APR of 2.5%. So that's another thing the question tells us. But Connor's going to pay it back per month. But we've worked it out from B part 1 that 2.5% APR is the same as 0.2060% per month. So we have that worked out, no need to redo it. Connor's paying the mortgage over 25 years and he wants to pay it monthly, so we're timesing that by 12. So Connor's going to have 300 monthly installments. So I'm basically just writing down everything we know. So this was our first part. Then we figured out how much Connor needs for his mortgage. Then we worked out his interest rate. And then we worked out how many installments he needs to make. Next thing I'm going to do though is go to my log tables on page 31 and take down the amortization formula, which is giving as A is equal to P times I times 1 plus I to the power of T or N, the power, which is going to be the amount of years, over 1 plus I to the power of N minus 1. So that's the formula from page 31 in my log tables. And filling that in now, A is basically going to find us the monthly installment. So the A stands for the installment. The P stands for the lump sum, the mortgage amount, which is €442,510. So that's the P. The interest rate is I, which is 0.002060. So again, we're dividing this figure here by 100. I'm then multiplying that by 1 plus I, which is 1 plus 0.002060. Now you can use your sequence method if you prefer. I'm using the formula here. And the power of n, which is 300 installments. That's all over 1 plus I to the power of n, so that's 1 plus 0.002060 to the power of n, which is 300, subtract 1. So calculator work here, that's giving me out an installment of €1,978 and a decimal of 93976. The question wants us corrected 2 decimal points, so that's our cents basically. So an annual installment of €1,978 and 94 cents. That's how much Connor needs to pay each month for his regular payment. And that's the end of question 10. If you have found these solutions to the mock papers of help to you, I'd be very grateful if you could subscribe to the Tulla Maths YouTube channel.